It's a great honor to me to give a talk at the International Conference on Basic Science. Today I will talk about the regularity of harmonic map between the metric space. Okay, my talk will divide into the three parts. In the first part, I give an introduction for this topic. And because we talk about partial differential equation on metric space, this partial differential equation is a harmonic map. So the main purpose in this talk, we talk about what's the regularity we can expect to this map. One is talking about what's the interior regularity and boundary regularity. Now we come to the first part. Now I consider two manifolds. One manifold is two manifolds. One manifold is n-dimensional Riemannian manifold with a matrix G. Another manifold is a k-dimensional Riemannian manifold N. And we consider C1 map from map U from the Mn to Nk between the two manifolds. Then we can define what's the energy by this definition. Energy, the integration for EU over whole manifolds. EU is the energy density given by actually the tangent map, the norm, the square norm of the tangent map. So in local coordinate is given by this expression. A critical point of the energy is called a harmonic map. In particular, a local minimize of this energy is called minimized harmonic map. In a special case, when the target manifold N is a real line, the energy is usually or dirichlet integral, the so-called energy of the ordinary energy. So harmonic map is extension of the harmonic function from the one function to a map. Actually, harmonic map is a nonlinear version of a harmonic function. Now, in order to write down the equation for the harmonic map, so usually the one easy way we can embed the target manifold in a higher dimensional Euclidean space RL. Now the energy EU can be written in this form. In this form, then by a direct computation, the usual computation or by the computer, the critical point of this functional is the Euler-Lagrange equation. This Euler-Lagrange is a weak solution for the following equation, partial differential equation systems. So actually, this is an elliptical type of system because this metric, because the coefficient here, the high order coefficient here come from a metric. It is a positive definite. So this is a elliptical type of equation systems. And the nonlinear equation because it is a quadratic term, nonlinear quadratic term in the second term. And AR is given by the second fundamental form of the target manifold in the high dimension Euclidean space RL. So this is the Euler-Lagrange equation. So we talk about the harmonic map. Actually, we talk about the solution, weak solution of these equations. The regularity of harmonic have a long history. Is one of the important topics. Oh, sorry. in the geometric analysis. They have a long history. Even in the this list of some of the known results. In the 1948 by Morlier, he proved every energy minimized harmonic map is smooth if provided that domain manifold is two-dimensional. And if the target manifold is a non-positive curvature, then is this is the harmonic manifold is also smooth. And in the 1982, the general regularity theorem was given by the Xiping and Ullenbeck. In this talk, I will in main purpose in this talk I will talk about regularity for a metric space into another metric space. We always talk about the target space with a non-positive curvature. So I would like to mention these results of this theory by the Yields assumption and by the Heath-Brown. If the target manifold has a non-positive sectional curvature, then any energy minimized harmonic map is smooth. I would like to give a remark. Without any restriction on the target manifold, an energy minimized harmonic map might not be even continuous. So if the target manifold is not have some positive curvature, the harmonic map may be non-regular. So one of the usual conditions for get the regularity, we need impose the target manifold is a non-positive curvature. Now I talk about now I would like to we talk about what's the harmonic map between the singular space. In 1992, Gromov assumed initiated the study of the theories of harmonic map between the singular space. Now I begin with the definition of the singular space. Actually, there are lots of the singular space, but we restrict our attention to a class of the metric space. This metric space have some sense of the some sense of the curvature. A metric space in here, I will talk about a metric space. This metric space, this is a topological space with a distance function. For a distance function, for any 2 points, we also assume this distance function is a length space. Means given any 2 points, we can realize the distance by a curve. This is the shortest curve, the geodesic. So we consider the length space, and we call this length space have a curvature bounded from below by some constant k. What's the meaning here? This meaning for arbitrary given 3 points in the metric space X, P, Q, R, and we connect each 3 points by a shortest geodesic. And we call this triangle. This is a triangle in the space X, the metric space. And because this triangle, we can consider a k-plane. What's the k-plane? This is a simply connect space, two-dimensional simply connect space of with constant curvature k. If the k is positive, this is a sphere. If the k is negative, it is a hyperbolic space. And if k is 0, it is a plane. Then we consider and the corresponding 3 points with the corresponding triangles of P tilde, Q tilde, and R tilde with the same length. This corresponding length. This is corresponding. We say this is corresponding triangles. When we say what's the meaning of the curvature is bounded from below by K. This means we consider middle point between the QR, this is the H, and corresponding middle point of the Q tilde and R tilde, this H tilde. If the length of the PH is bigger than or equal to corresponding P tilde and H tilde, we say this space has curvature bounded from below by K. This means we're using the topological comparison theorems to give the definition of what's the curvature bounded from below of this metric space. Now, there are lots of examples for the Alexander space, the Alexander space with the curvature bounded from below. For example, the Riemannian manifold, orbifold. This orbifolds with a sectional curvature bounded from below by K. This is the Alexander space with curvature bounded below. The convex polyhedrons. This is the curvature as non-negative curvature. And you can if the group action X isometrically on a manifold, you consider cosine space. Then maybe is not need to free action. So this is the cosine space maybe have somewhere is not topology. Topology is not like a manifold. So this is also a Alexander space. And in using we say the curvature bounded from below by K. We also by saying the definition, the similar definition, we can say what's the metric space is bounded from above. If the curvature bounded from above by 0, we say this is a non-positive curvature. We space a non-positive curvature. In particular, sometimes we say this is the Hardeman space. Sometimes we say the Ket0 space. Ket0, it means the Gadan, Alexandrov, and Toponogov. So Ket0 space. For example, the Ket0 space, the simple connect Riemannian manifold with the curved sectional curvature non-positive is Ket0 space. And another one we look at this picture is a tree. It's the water metric. This is also the non-positive curvature, and this is the building. So in our definition of the non-positive curvature, Ket0 space, the most useful part is maybe it's not locally compact. So for example, there are this little tree, there are lots of the branch here, maybe an infinity over branch. So including of the non-locally compact case. Now I will talk about what's the singularity on Alexander space. What's the singularity for Alexander space? This Alexander space, it can be proved at any point. We can dilate this point. Dilate this point, we can, in the sense of Gromov-Hausdorff sense, we can take a limit. This limit is also a metric space. This is also not only the metric space, it's also as a cone have a cone structure. If we say this is the tangent cone. If the tangent cone is not isometric to the Euclidean space, we say this is a singular point. For example, we look at the cubic, and each corner point is a singular point. For that, we look at another point. Look at another example is the cone over the RP2. The vortex is a singular point, and not only the singular point. Actually, this singular point is not topology is not manifold. It's a topological singular point. So one can ask a question: how large a single point for Alexander space. If we will denote by the x, this is the set of the all single points in an Alexander space. It was proved by the Blago, Gromov, and Perelman in 1992. The dimension of the single point, the part of a single point, has a codimension 2, at least the codimension 2. But and on the other side, can give examples by the Osu Ashioya in 1994. So some examples of the single point set, the set of single point, may be dense in the disk space. This means that the regular part is not open set. Now this is use this these are the metric space. We talk about the metric space of Alexander space. Now I consider second part of the regularity of harmonic into a singular space was first studied by the Gromov and Xun in 1992. This following theorems was proved by Gromov and Xun. The theory state as following. Let U is be an energy minimized map from a domain is a smooth. Domain is a smooth manifold, and target is a non-positive curvature of in the sense of Alexander space. They prove that any energy harmonic map is always locally ellipse map. Because we consider in a metric space, the best regularity one can expect is a ellipse regularity. So they get a ellipse. Also the ellipse regularity is a very important part in the further study by the simple rigidity of some group theorems. Because we using the ellipse regularity, we can establish some kind of the Born formula. We can establish some of the vanity theorems on this topic. Now, the Gromov and Xun consider domain is smooth. And if the domain is not smooth, if a domain is also a singular, the domain is a bounded domain in Alexander space, and target is Alexander space with non-positive curvature, cat zero space. This was proved by the Yost Fanghua Lin. They prove any energy minimized harmonic map from the singular domain to the target is all singular, is locally hold continuous. Now, and natural questions. Based on above Gromov and Xun theorems, Fanghua Lin and Yost posed the question conjecture. They say if the domain is Alexander space and target is Alexander space with non-positive curvature, they ask the question: is energy minimized harmonic map from omega to y is locally ellipse continuous? Now, to understand this question, let me answer the questions. Let me consider a simple case. Because the domain is singular, target also singular. Now we look at a simple case is the harmonic map from a special case is only a bounded domain in Euclidean space and with the singular metric. To another one, we can easy case or to another one, the target is smooth. If a domain is a singular, the target is smooth, then we can write down this map satisfy an elliptical system. This is Euler-Lagrange equation of the harmonic map in this form. In this form, this comes from the metric, domain metric. And A alpha is the second manifold of the target manifold. This is smooth. So the main problem is the coefficient here is maybe non-continuous. This is singular part, this is singular part, and this is also singular part. And in this case, if the domain, this coefficient, if the L infinity, this bounded coefficient, it was proved by the Shi Yu Guang. Using the George Nash-Moss iteration argument, one can conclude that U is whole continuous. One can expect this case because this divergent form also. This is a divergent form of the Xiping system. The coefficient is bounded coefficient. Then by using Nash-Moss iteration, by the George Nash-Moss iteration, one can expect to get the whole continuous. But if the coefficient is the coefficient may be not continuous, even the coefficient is continuous, the U might fail to be Lipschitz continuous. We can look at the following examples. This following example is given alpha by this function. By using this function, R is the in the polar coordinate, R is distant from the origin. And using the in the Aij, this is in this form give out the metric. In this way, we get the metric, and using the metric, we can say this is a harmonic function. This is a harmonic function. U is this coefficient. Satisfy this harmonic function. In this way, satisfy this equation. But the derivative also not belong to is bounded. This is not Lipschitz function. This is not Lipschitz function. So this give our examples. What's we cannot expect a divergent form in Lipschitz systems. The coefficient is continuous, but the solution in how to get a solution is Lipschitz. Cannot expect these results. Now, come back to our case, the Alexander space case. Because our domain is Alexander space, we look at the P is a regular point. That in the regular point, we can use a local coordinate. We can get the metric is actually metric coefficient is the PV function. So it's not continuous. So it's well known this is not continuous, maybe on the dense open set. Thus, it appears that the answer to the above the Ross-Lin conjecture might be negative. On the other hand, we consider a concrete examples due to Chen Jiyi. We look at the two-dimensional metric space, a metric cone. This is a two-dimensional metric cone. In polar coordinate, the metric write down in this form. dr squared, r is the distance from the origin. Theta is the angles of the two planes. In the polar coordinate, the usually Euclidean metric is the coefficient here a equal to 1. This is the Euclidean metric. If the a is bigger than y and less than y, also a Riemann metric. But in this metric is the we have a singular point in the origin. In this metric, U equal to R 1 over A cosine theta is a harmonic function. If A is less than 1, less than or equal to 1, this matrix is Alexander space with non-negative coefficient. If A is less than or equal to 1, because R is the distance from the origin. So this is the Leibniz function. But on the other hand, if the A is bigger than 1, the matrix is a metric cone. The flat outside everywhere is actually flat outside the origin. The only have a negative infinity curvature in the origin, in the vortex. And this harmonic function is not Leibniz continuous. So these examples tell us the curvature condition on the domain is a very important condition for the conjecture. Now, the above two examples shows the answer to the Lins conjecture should be subtle, maybe correct or maybe not correct. In 1980, in a joint work with my colleague Zhang Huichun, we obtained an answer to the Lin conjecture. Our answer here, we prove the Lin conjecture is right. We prove if the omega is a domain, boundary domain in Alexander space, with a curvature bounded from below by some constant k, and the target is a capital zero space, then any harmonic map, any harmonic map is locally Leibniz continuous. Moreover, we can get a gradient estimate. This depends only on the curvature, only on the dimension, only on the oscillation and on the energy of on the domain. This is our gradient estimate. Now, moreover, not only get the Leibniz continuous, we can also get a Bochner type inequality. This is Bochner type inequality here. You also get a Bochner type inequality. Recently, I have a two group of papers. Group of people, one by the Mondino and Semola in 2024, and by Gigley. Another one is by Gigley. They can extend our results to the more general of the metric space. This is called the generalized rich curvature boundary from below of the curvature in the RCD space. We can generalize our results for the more general to the more generalized of the metric space. Now I come to the third part of my talk. Is about boundary regularity. The boundary regularity also we would like to recall of the classical results by the Schum-Ullmann. The boundary regularity theorems by Schum-Ullmann prove the flow results. If consider M is a smooth manifold and the boundary is C2 alpha, and we consider target is a smooth manifold, then suppose we have minimized a map, minimize harmonic map, and suppose that the boundary value is a C2 alpha. This is boundary value. They prove the harmonic map not only on interior is smooth, and in the boundary, and all the boundary is the full neighborhood of boundary, you also see C2 alpha. This means once we have a smooth boundary, a smooth data, then the solution also a smooth allowed boundary. actually is different from the interior in the regularity. Interior again, we also need to allow we have a restriction and the target manifold on target manifold of the curvature sign, and the boundary regularity is arbitrary. You can get always have a regularity in here. Now we are consider the irregular domain. For example, we consider the domain is a Lipschitz domain. Sometimes some sense of Lipschitz or more general domain, irregular domain. And we also the data, because we consider metric space, the best data we can say this is the Lipschitz data. So what kind of the locality we can expect for this singular domain? We also consider domain is Alexander space, or more generally we can consider RCD space, and target is a cap zero space, non-positive curvature. And we also always assume, and the assumption of the boundary data is Lipschitz. The question is what is the regularity of the harmonic in the full neighborhood for the boundary of the partial omega? Now, also have a long history study on the harmonic map of what's the boundary regularity along the boundary. We record the special case of harmonic function in the Euclidean space. We look at that this D is a bounded domain, and U is a harmonic function. This solution, a W12 solution, with the boundary data. Boundary data is phi belong to Lipschitz function. Now, if the boundary, what kind of assumption of the boundary? If the boundary is Lipschitz boundary, this means the Lipschitz or is known. That is the solution because the boundary data is Lipschitz. So the Lipschitz boundary, there was no this U is C alpha, but hold continuous for some alpha. It's not every alpha. So for some alpha, if the boundary is Lipschitz, one can expect the locality is hold continuous for some alpha. And if the boundary is improved, locality is not just Lipschitz continuous, we can say this boundary is C1 or C2, the smooth boundary. Now, smooth boundary, one can say this is the hold continuous for every component 1 minus action, for every action bigger than 1, back to 0. However, one cannot expect this Lipschitz continuous, even the boundary is smooth. This is due to classical examples of the Hardy-Littlewood in the 1930s. So the regularity of the harmonic function for the irregular domain, the boundary regularity is very sensitive. Depend on what's the condition on the boundary. Even the data is smooth. Data is Lipschitz continuous. Now, because we consider metric space, metric with a local structure, metric space is not usually maybe have some point in metric space. The local structure is not manifold structure, so we usually cannot say what's the Lipschitz for it. So, in order to say conditions, we can say this following type of the conditions. One type is the exterior density condition. What's the exterior density condition? If for any boundary point, and we give the ball with the center at this boundary point with radius r, if the measure, the volume in this ball minus the outside of the domain have have a one portion of the whole volume, we say the exterior density condition. And we say with another condition, parametrically regular condition. Parametrically condition, this means in some sense we have the boundary measure. This boundary measure is like to the usual Hausdorff measure. This is means the boundary is higher. For example, for a Lipschitz boundary, always have satisfied the parametric regular condition. And another condition, we say the uniform exterior ball condition. This means for every point in the boundary, we have a fixed radius of the ball outside this domain. So for a general metric space, we consider three types of conditions. One is the exterior density condition, another is the parametrically regular condition, and also another one of the uniform exterior ball condition. Now, while recall some results, it's easy to know. If the omega is Lipschitz, then it automatically satisfies the parametric regular condition, and also satisfies the exterior density condition. So in some sense, the parametric regular conditions and exterior condition corresponding to the smooth case of the Lipschitz domain. Another one is if the C2 conditions corresponding to exterior ball conditions. And in 1994, to my knowledge, the first results on the singular domain on the harmonic map case of the singular harmonic map case by the Xiping the results for him. These four results is if the boundary domain in a manifold, domain is a smooth manifold, and target is kept zero. And if the domain is not regular, just Lipschitz domain, the proof is C alpha to some small alpha, some exponent of the whole continuous. This corresponds to the harmonic function case. This means generalized harmonic function results to the harmonic map. And another one is C1 corresponding to the whole continuous for every exponent less than 1. The whole continuous for every component. Now, our first results in the last year, in a joint work with my colleague Zhang Huichun, we proved further results. We consider, because the Sabinowski consider domain is a smooth case, we consider domain is not smooth. In the domain in RCD space or Alexander space, and target is the cap zero, and the boundary data is Lipschitz. We prove if the domain the boundary of a domain is satisfies the exterior density condition, then this is a solution that the harmonic map is hold condition for some component, some hold exponent. And if the domain satisfies the uniform exterior ball conditions, then we can prove this is the hold continuous for every exponent of 1 minus action. I also want to remark, even in the smooth manifold case, one cannot expect this is Lipschitz continuous. We only get this is C1 minus action of the whole continuous. Why? Now I would like to record classical examples by Hardy Littlewood. Hardy Littlewood examples here we explain as following. If the D is a unit ball in the two-dimensional, just consider unit ball in the two-dimensional in the polar coordinate, our fate in the polar coordinate, the unit ball, and we call the boundary data. We consider boundary F0 is defined on the boundary of the unit ball of boundary. This is the circle x1. This function given by sine absolute value of sine theta. If the theta less than equal to 1 pi over 2, and because other part of the f0 theta, f0 the function is equal to 1. So this is a Lipschitz function. Our boundary is the Lipschitz function, easy as tan to the whole disk of the whole disk. So this get the boundary data is the Lipschitz data. And use this data, when the harmonic function, we use the data, we can use it by the Poisson integral formula, write down the harmonic function with this boundary data. You use this is a green function formula, the Poisson integral formula. This is there by direct computation is easy to computation. By a direct computation, one can say this function is not Lipschitz function. The gradient of this harmonic function and the boundary have a low bound here. So this give our examples. Even the smooth boundary, but the boundary data is Lipschitz. The solution harmonic function is not smooth. Even is not just smooth, even not Lipschitz. So next thing I would like to what's the question? Question in a sub boundary regularity. So what kind of can expect? Can one expect a sub boundary regularity? So our question is, can one expect the boundary regularity is to like to growth like that? In some sense, the boundary is BMO function on the boundary. And this is true if the boundary is a smooth case. If the boundary is a C2, if the boundary is C2, is a smooth case, one can flatten the boundary by using the transformation of the boundary, flattening this boundary. We can use it as some fraction, a reflection of the function, and it become the interior. We can use the above our expression using the of the Poisson integral formula, write down the solution, so that we can show this. Because the boundary using the flattening, because the boundary is C2, so after flattening, the coefficient is smooth, the remain to the smooth. So the main point is relevant. But the main difficulty here, if the boundary is just Lipschitz, after flattening, the coefficient may be singular. The coefficient is singular, you cannot use the usual Poisson integral formula. We need to establish another type of the green function and Poisson integral formula. So the main difficulty in here. So I would like to mention the recent laws in the John Walker or in the Zhang Guichun in this year. We prove here. Our second result on the boundary is a affirmative answer to the above questions. we consider X d mu be RCD space, and this means the metric space which generalize of a logical boundary from below. The bound below by logical boundary by curvature K, and the dimension boundary from above by N. And Y is a cap zero space. And we assume the domain is a parametric regular condition. This sometimes corresponds to Lipschitz condition, Lipschitz boundary value condition. And also assume the uniform ball condition. And then give any boundary data is Lipschitz boundary data. And then harmonic map with this deletion boundary data of U0, we can get the gradient estimate, Lipschitz gradient estimate by using this formula. In here, the delta x is the distance from x to the boundary. So this is just our aspect to this type of the estimate. This I will not give a remark on our results. Even because we have a long history of the study on the harmonic function is not harmonic map. Harmonic function on the irregular domain of the Euclidean space, even for the Euclidean space. So our result even is new for harmonic function on the Lipschitz domain of the Euclidean space. In particular, our result tells us if the domain is the Lipschitz domain and satisfy uniform exterior ball condition, if the data, the boundary data is Lipschitz boundary, then also bounded by this growth, by the log of the 1 over the distance between this point x to the boundary. So even we get the regularity for the more general case of the harmonic map between the singular space, even come back to the very special case of the smooth case and the Euclidean space, and but the domain is just Lipschitz continuous. This is also a new result. I think I should stop here. Thank you for your attention.
Okay, any question?
Yeah, thank you for the very nice talk. So for your theorem 2a, can you replace this this density condition by the capacity density condition?
Capacity condition, yeah, you're right. Yeah. Actually, we can. Actually, our statement is capacity conditions, but we're easy to
State.
State. Yeah.
Yeah, thank you.
Any further question? If not, let's send the speaker again.